welcome to the channel Physics by IITians, where we learn physics, understand physics for cracking examinations and interviews. We shall continue our atomic physics lecture. Today I shall discuss the spectroscopic terms and their notations, doublet structure of the alkali spectral lines, fine structure of the hydrogen spectral terms, and I shall discuss in another lecture series about anomalous Zeeman effect. So before starting the spectroscopic terms and their notations, we should know what is the meaning of terms and what is the meaning of term value. So the term means the energy levels of the electrons of an atom are called terms of the atom, and the corresponding energies expressed in wave numbers that are called term values. So suppose one electron atom. So one electron atom basically like hydrogen like atom. Okay, they have one electron in the most outer shell. So the energy levels corresponding to one electron atom, it can for L values can be 0, 1, 2, 3, 4. So L values, for L value 0 it will be denoted as S, L is 1 it will be denoted as P, for 2 it is denoted as D, 3 it will be denoted as F, 4 it will be denoted as G. So for 0, 1, 2, 3, 4 it will be S, P, D, F, G. So by spin orbit interaction, we already discussed about spin orbit interaction in the previous video. That is, the total angular momentum J will be the vector addition of the orbital angular momentum and spin angular momentum, and J can have values from L plus S to mod of L minus S. So suppose for the one electron atom, S will be half or minus half. So L plus S is L plus half, or L minus half is L minus S is L minus half. So there is the 2s plus 1, this term is called the multiplicity. So this is the spectroscopic notation to find out the spectroscopic term values. Here it is 2s plus 1, this is the L value, and this is the total angular momentum J. 2s plus 1 Lj, where 2s plus 1 is the multiplicity. So for one electron atom, 2 into s plus 1 will be 2, because 2 into half plus 1. Okay. So the term values for the SPD, different L values. So for L equals to 0, this will be S, and J is half, because L plus S, that is S can be spin half, so it is half. So this will be 2s half, because it will denote as 2s plus 1, and this will denote as L, and this is J value. So we get 2s half. For L equals to 1, the term is P, and we can have two J values, that is 1 plus half and 1 minus half. For 1 plus half it is 3 by 2, for 1 minus half it is half. So we get two different notations or spectroscopic notations. So this will be 2s plus 1 will be 2, and for L equals to 1 we get here P, and J is 3 by 2 and half. So 2p 3 by 2, 2p half. Similarly for D term, L is 2, so it should be 2 plus half and 2 minus half, that is 5 by 2 and 3 by 2, and this is half. So the multiplicity is 2s plus 1, that is 2 into half plus 1, that is 2, and for D, L equals to 2, this is D, and this is 5 by 2, 3 by 2. So I think you understand that how to find out the spectral notations or full notation of spectroscopic term values of energy levels. Okay. Now we shall understand the arrangement of the electrons in the atoms. We do it by Aufbau principle. Sorry. So here the first is 1s, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s. This all we know, the energy levels. So electron will first fill the in the lower energy levels, then it will go to higher energy levels, and the filling will be according to the Pauli exclusion principle. This all the energy levels will be filled according to the Pauli exclusion principle, and it will be denoted by the four quantum numbers n, L, ml and ms, where these four quantum numbers cannot be same for the two different electrons. If n, L, ml are all same, ms should be different, either it is plus half or minus half. Okay, So you all know these things. So we shall now find out the ground state of different uh, elements like inert gas. What is their ground state? They are closed shells, so their ground state is 1s0. For alkali atoms like lithium, sodium, potassium, rubidium, they have the outermost valence electron is s electron, and this shows the doublet structure, and the ground state is 2s half. Alkaline earth group, that is beryllium, magnesium, calcium, strontium, they have two valence electrons in the outermost s subshell, that is L equals to 0, and ground state is 1s0. For Z is elements like Z equals to 5, 13, 31, 49, 81, they are trivalent and their ground state is 2p half. So all these are from like Z equals to 5. How you get 2p half? 1s2, 2s2, 2p1. Okay. So 1s2, 2s2, 2p1. Here this is the outermost electron, that is 2p1. Now this p equals to L equals to 1. So this value L value is 1, that is p. Now s equals to half. Okay. So 2s plus 1 will be 2 into half plus 1, that is 2, and j will be s plus L, or you can write it as L plus S to L minus S. Now we are seeing that L plus S will give us that 1 plus half, and L minus S will give us 1 minus half. So 1 plus half is 3 by 2, 1 minus half is half. So this term, that is 1 by 2, it will give us the ground state. Okay. This will be all we have to follow the Hund's rule also. In another video lecture, I will also discuss about the Hund's rule. Now we should look at some more elements, like the elements which have outermost electronic configuration as NP5. So the ground state is 2p half. Energy levels of complex atoms, if they have two non-equivalent electrons. Non-equivalent means the different values of n and L, or both can be different. Either n can be different, L can be different, that is principal quantum number is different, azimuthal quantum number is different, or both can be different. You have to do, that is the vector addition. How do you do that? Suppose you have given two non-equivalent p electrons. So the possible values of the total spin, that is s, can be half plus half, that is both are parallel, or s can be half minus half, that is they both one is parallel, another is anti-parallel. Okay. So now for L equals to 1, because both are p electrons, so possible L values are 0, 1, 2, because you have to add L1 plus L2 to L1 minus L2 to get the possible L value. So L1 plus L2 is 2, L1 minus L2 is 0, so 0, 1, 2 we get. Now the spectroscopic notations are, for S equals to 1 we get 3s, 3p, 3d for L value 0, 1, 2, and for S equals to 0 we get 1s, 1p, 1d for L values 0, 1, 2. These are the case for the non-equivalent p electrons. These are the cases. Now for two equivalent electrons, what will happen? There will be certain boundary exclusion principle, that is Pauli exclusion principle. It will be considered here, because the two equivalent electron means that both n and L are same. Okay. So they have same n number and same L number. So you have to, definitely you have to apply the Pauli exclusion principle, and you will not get all the energy levels like the non-equivalent energy levels. Some of the energy levels are allowed and some of the energy levels will not be allowed. So let us take the same case for the two equivalent electrons, that is two equivalent p electrons. Now L is same, so Ml is same. So due to the L and Ml are same, N is also same, so Ms must be different, and this is either Ms equals to, both of one will be up, one will be down, that is half and minus half. So S is 0, so we get only 1d term. Okay. Here if you take L equals to 2. Okay. Now look here, here is a table where the energy levels between two equivalent electrons and the two non-equivalent electrons are given. So E is the equivalent electron term and N is non-equivalent electron terms. If both the electrons are from S cell and they are equivalent electrons, then you get one S term. But if they are non-equivalent, you get two terms, one S, 3S. If both P electrons, okay, then for equivalent you get 3 energy levels, for non-equivalent you get this energy levels more than 3. So same with D, 2 equivalent D electrons or 2 non-equivalent D electrons. Look at the difference in the energy levels. In equivalent energy levels there are certain energy levels are not allowed or forbidden due to the Pauli exclusion principle. This is also some spectroscopic term notations. For single S valence electron like hydrogen, sodium, potassium, they have 2s half. For single P valence electrons like boron, aluminium, gallium, etc. So P valence electron, S valence electrons, single means that there is only like hydrogen, that is 1s1, okay. So this kind of thing. So in the P sublevel there is only one electron for the single P valence electron. Now 2s valence electron, this is 1s0, and 2p valence electron, this is 3p0, like carbon, silicon, germanium, etc. So look here, the energy, spectroscopic energy values are different for the different combinations or different states. That is the most important thing, that with the spectroscopic term values or term notation, you are directly getting the information about the spin, about the multiplicity, about the total angular momentum, about the L value, okay, or you are getting the information about the energy levels of that atom. Now here, like the last time which I discussed, that 1D term was only allowed, and in the earlier case we get 1D term as well as the 3D term, where for the equivalent electrons 3D term is not permissible. So permissible terms are 1s, 3p, 1d for the 2 equivalent p electrons. Now for 3 electrons, suppose there are 3 electrons, how to find out the resultant L? What you have to do, you first take the individual L, that is L1, L2, L3, then you take the combination of 2, that is vector addition of 2. You find out, suppose this is capital N1 and this vector addition, that is L1 plus L2 to up to L1 minus L2, then you add the vector addition, suppose this is L3, the another one, and you should vector addition do this to the L1, that is the resultant of the 2, that is L3 minus mod of L1. So I think you can understand what I am trying to tell, that for the 3 electrons, L and S values of the third should be combined with those of the other 2 subject to the Pauli exclusion principle. So any 2 you first combine, vectorially add them, you get a resultant, then you apply the vector addition to the third one with that combination. So now for closed shells, which I told you, like the inert gases, the ground state is 1 is not, because Ms is also 0 there, Ml is also 0 because L is 0 there. So the ground state is 1 is 0, because S is 0, L is 0, J will be also 0, and 2S plus 1 will be 1, and L equals to 0 means it is a S value, S term, okay. Now doublet structure of the alkali spectral lines. We have to understand why there are 2 lines or doublet lines in the spectral lines of alkali atom, like the hydrogen atom, like the sodium lines D1, D2. Why we get this doublet line? So these lines, these spectral lines have doublet structure, and it arises due to the electron spin. Okay, how is it? What is the physics behind it? Suppose or consider the magnetic interaction between mu L and mu S, where mu L is the magnetic angular magnetic moment due to the angular motion of the electron, and orbital motion of the electron, and mu S is the magnetic moment due to the spin motion of the electron, okay. So this interaction causes a difference in energy level between the two terms of the same L value, that is J equals to L plus minus half. So now multiplicity is 2s plus 1. Now if also you remember, if L is greater than S, then multiplicity is 2s plus 1. If L is less than S, then multiplicity is 12 plus 1. Lower value will be added as a 2 into lower value plus 1. Now look here, what will happen for the case of doublet structure of sodium, that is D1 D2 line. We know the sodium energy level as 1s2, 2s2, 2p6, 3s1. So the principal series for the sodium line is Np to Ns. Okay. In also alkali spectral lines, we have discussed about the principal series, the diffusion series. We have already discussed. Okay. Sharp series. Please watch that video if you haven't discussed that. So the for the L equals to 1, this is for suppose the electron is at 3 level. Okay. So that is the excited level, and electron is at 3p level. For 3p level, L equals to 1. So p term, so J values can have two different values. One is L plus half, another is L minus half. So this can be 3 by 2, this can be half. Now 3 by 2 will give you the term 2p 3 by 2, and half will give you term the 2p half. So this selection rule for the transition is delta J equals to 0 plus minus 1. In case of D lines, we get that 2p half to a transition of 2s half, and 2p 3 by 2 to a transition of 2s half. So let us see this in this diagram. So this is, I think this is hydrogen, this is another diagram. Okay, here this is the diagram, this is our sodium line. I have another diagram here. So this is the spin orbit splitting or doublet structure. This is the 3s half line, this is 3p half line, and this is 3p 3 by 2 half line, 3 by 2 line. So the transitions is one from 3p 3 by 2 to 3s half, and 3p half to 3s half. These are the two different lines. One is D1 line, another is D2 line. And this is responsible for the doublet structure, that is spin orbit interaction. If you don't have J values different due to different L and L due to the L plus minus S values, that is L and S is the interaction between orbital and spin angular momentum. Now we understand what is the fine structure of the hydrogen spectral line. How to find out the fine structure of the hydrogen spectral lines? We have considered that Sommerfeld tried to explain it by considering the relativistic variation of mass of the electron, but it was a partial success. We have seen that it cannot explain all the spectral lines. Now quantum mechanical calculation of the relativistic variation of the mass will certainly give some correction to the Sommerfeld calculation, and it gives the value for the relativistic correction is minus m into z square e to the power 4 by 32 pi square epsilon naught square n square h cross square z square alpha square by n square into n by L plus half minus 3 by 4, and this is valid for hydrogen like atoms. Now you have to also consider the spin orbit coupling with this relativistic correction, which Sommerfeld didn't do that at that time. So now the modern physics, what includes with the relativistic correction, we need to add this spin orbit coupling or LS coupling interaction term, that is delta E, and this will be certainly give our delta E or energy difference value as minus m z square e to the power 4 by 32 pi square epsilon naught square n square h cross square into z square alpha square by n square n by j plus half minus 3 by 4. Okay, this alpha is fine structure constant. Now look at this formula. You have to understand the dependency. Here, what are the constant terms like m, j, z, e to the power 4 pi? These are the constant terms. The variable terms are n and j. For the same n value, the variable is only j. Okay, so it depends only j. Now same for the two consecutive L value, it has a problem that the value of this energy level is only depend on j. So if you have certain values like 2s half, 2p half, look here, they all have same j values. So according to this formula, that is, they should have the same energy level for the same n value if their n is also same. So j values are also same. So these two labels have same energy value. Also this two term, that is 2p3 by 2, 2d3 by 2, they have also same j values. So they have also same energy if they have same n values. So this was a problem, and this problem was finally solved by considering the interaction between the electron and radiation field, because experimentally it was uh, observed that this energy levels cannot have same values, although they have same n, they have same j values, but they are different energy levels. And this was only explained by taking the interaction between the electron and the radiation field, and it shows that the same j but different l do not have same energy, although they have same values, but they have different l and they have different energy values. And this was done by a experiment, sophisticated experiment performed by Lamb and Rutherford in 1950. What they showed, they take the hydrogen atom and they find out the energy level difference of 2s half and 2p half. Look here, the j values are same, n values are same, only l values are different, and they find out the energy level difference delta E by H, or in terms of radiation they find out as 1058 megahertz. Okay, so this are the explanation for today, that is the hydrogen atom fine structure, and then why we get different values for the doublets. And earlier I also discussed about the spin orbit interactions. So next video we shall discuss about anomalous Zeeman effect, what are the z factor here, and what are the main Paschen back effect, so Stark effect. So for now this is enough. Thank you for listening. If you find this video helpful, you can support us. You can support us by clicking the link in the description box. Also don't forget to subscribe our channel. We get different videos which will be benefited for you, and you can also join our Telegram channel. Thank you.